The X-20 Dyna-Soar was an ambitious United States Air Force project in the early 1960s. It was designed as a reusable military spaceplane capable of orbital missions. Although it was never launched, the program influenced future spacecraft and military planning. Dyna-Soar represented the merging of aircraft engineering and spaceflight technology. The project aimed to give the U.S. a rapid response orbital platform. Missions included reconnaissance, satellite interception, and potential strike operations. Its sleek design promised maneuverability in space unlike any prior vehicle. The program embodied Cold War ambition at the edge of technology. The X-20 Dyna-Soar originated from late 1950s U.S. Air Force studies for orbital reconnaissance and tactical strike capabilities. Military planners wanted a reusable spaceplane that could perform rapid orbital missions. The concept combined aircraft-like maneuverability with orbital flight. Engineers envisioned a vehicle capable of gliding back to Earth after completing its mission. Early design efforts drew heavily from experimental X-series aircraft. Data from high-speed flight, reentry tests, and lifting body research informed the project. The goal was to create a vehicle that could operate both in space and the upper atmosphere. Success depended on integrating aerodynamics with heat-resistant materials and control systems. The program remained highly classified, with only top military and scientific personnel aware of its existence. Its missions included reconnaissance, satellite interception, and potential orbital strike options. Secrecy limited public knowledge and press coverage. This allowed engineers to explore radical design choices without scrutiny. Boeing was awarded the main contract for the program. The company began wind tunnel testing, structural design, and materials research immediately. Titanium and stainless steel alloys were tested extensively for reentry. The project pushed the limits of contemporary aerospace engineering. Designs emphasized orbital maneuverability and safe atmospheric reentry. The spaceplane's delta-wing configuration allowed both lift during reentry and control in thin atmosphere. Guidance and control systems combined automatic functions with pilot input. Engineers faced unique challenges in balancing weight, strength, and heat resistance. Despite never being launched, the X-20 program influenced future aerospace projects. Concepts developed for the Dyna-Soar contributed to the Space Shuttle and other lifting body vehicles. Its research validated piloted orbital flight and controlled reentry. The project became a critical stepping stone in military spaceplane development. The Dyna-Soar was a sleek, delta-wing spacecraft built for orbital maneuvering and controlled reentry. It featured a heat shield to survive the intense temperatures of atmospheric return. The craft's structure combined lightweight alloys with high-strength materials. Designers balanced mass with the need for onboard systems and payload. Guidance and control systems were highly advanced for the era. The vehicle was intended to be piloted manually for certain operations. Automatic systems would handle orbital insertion and reentry trajectory. Navigation required precision to ensure safe landing on a runway. The spaceplane's wings were engineered for aerodynamic lift during reentry. Unlike capsules, it could glide to a specific landing site. This capability allowed more flexibility than ballistic vehicles. Engineers studied reentry physics extensively to reduce thermal stress. Propulsion relied on conventional rocket boosters to reach orbit. The spaceplane itself carried no primary engines for orbit insertion. Orbital maneuvering would use small thrusters for attitude control. This separation of launch and spacecraft simplified the main vehicle design. Materials research was a critical part of the program. Titanium, stainless steel, and advanced composites were tested. The structure had to survive both vacuum and high G-forces during reentry. Every aspect of the design pushed contemporary engineering limits. The cockpit and crew systems resembled those of high-speed aircraft. Pilots would control flight surfaces during atmospheric flight. Life support systems were designed for orbital conditions. Human factors engineering was a major focus for mission safety. The X-20 was never fully launched, but its engineering informed later projects. Space shuttle lifting bodies, military spaceplanes, and orbital maneuvering vehicles borrowed concepts. The program proved the feasibility of controlled reentry. Dyna-Soar was ahead of its time in combining aircraft and spacecraft design. The X-20 Dyna-Soar was a sleek, delta-winged spacecraft built for orbital maneuvering and controlled reentry. Its structure combined lightweight titanium alloys with heat-resistant stainless steel. Engineers carefully balanced mass with the need for onboard systems and payload capacity. The vehicle's aerodynamic shape was optimized for both space and atmospheric flight. Guidance and control systems were highly advanced for the era. Automatic systems managed orbital insertion, while pilots could manually control reentry and glide. Attitude control thrusters allowed precise maneuvering in space. Navigation accuracy was essential to ensure the vehicle could reach designated landing zones. The spaceplane's wings provided lift during reentry, allowing a gliding descent to a runway. Unlike ballistic capsules, it could perform controlled maneuvers in the atmosphere. This capability increased landing precision and mission flexibility. Aerodynamic surfaces had to withstand extreme thermal and aerodynamic stresses. Propulsion relied entirely on rocket boosters for orbital insertion. The X-20 itself carried no primary engines for sustained orbit. Small thrusters provided attitude control and minor orbital adjustments. This separation simplified the spacecraft's main body design and reduced weight. Propulsion relied entirely on rocket boosters for reaching orbit. The X-20 itself carried no main engines, only small thrusters for adjustments and orientation. This allowed a lighter, more streamlined design. Engineers focused on optimizing the balance between mass and payload capacity. The vehicle's aerodynamic control surfaces allowed it to maneuver like a glider in the atmosphere. Unlike ballistic capsules, it could approach precise landing zones. This capability provided flexibility for military missions and recovery operations. Extensive wind tunnel testing verified stability and handling during reentry. Although the X-20 never flew, it left a lasting engineering legacy. Concepts developed for materials, control systems, and lifting body aerodynamics influenced the Space Shuttle and other spaceplanes. The program demonstrated that piloted orbital flight and controlled reentry were achievable. Its research laid the foundation for future reusable spacecraft designs. The X-20 Dyna-Soar faced numerous technical and programmatic challenges during its development. Integration of aircraft-like control with orbital flight proved extremely complex. Heat shielding for reentry required new materials and testing methods. Every design decision pushed the limits of 1960s aerospace engineering. Cost overruns became a significant concern as the program progressed. Advanced materials, specialized testing facilities, and custom components drove the budget higher. The program competed for funding against other emerging space initiatives. Political pressure mounted to prioritize projects with more immediate results. The rapid advancement of alternative missile and satellite technologies challenged the Dyna-Soar's relevance. Intercontinental ballistic missiles offered strategic strike capability without risking pilot lives. Reconnaissance satellites could perform many missions more cheaply. Military planners questioned whether the spaceplane provided sufficient advantage. Program management suffered from shifting priorities and inter-service rivalries. The Air Force, NASA, and Department of Defense all had overlapping interests. Coordination delays slowed progress and increased uncertainty. Decision-making often became politicized rather than purely technical. Testing and preparation were extensive but incomplete. Prototype construction and ground testing proceeded cautiously. Reentry simulations highlighted unresolved thermal and structural issues. Engineers struggled to reconcile ambitious performance goals with available technology. By 1963, leadership concluded that the program's costs outweighed its strategic benefits. The project had never flown and still faced major engineering hurdles. The Dyna-Soar was officially canceled despite years of effort and investment. Its termination reflected the shift toward unmanned and missile-based systems. Despite cancellation, the X-20 program contributed valuable knowledge to aerospace engineering. Research in materials, lifting body aerodynamics, and orbital guidance informed later spacecraft. Many concepts were directly applied to the Space Shuttle and military spaceplanes. The program proved that controlled orbital flight and reentry were achievable, even if never operational. The X-20 Dyna-Soar left a lasting mark on aerospace engineering despite never flying. Its research validated lifting body reentry and piloted orbital flight concepts. Engineers developed advanced materials, guidance systems, and control methods. These achievements influenced nearly every reusable spacecraft that followed. The program shaped the design of the Space Shuttle, particularly in aerodynamic surfaces and reentry techniques. Concepts for thermal protection and structural integrity were applied directly. Orbital maneuvering and precise landing capabilities became standard in later designs. The lessons of Dyna-Soar carried forward to military and civilian programs alike. Human factors and cockpit design principles were another enduring contribution. Pilots' roles in navigation, reentry, and emergency procedures informed crewed spacecraft standards. Redundant life support and control systems influenced NASA and Air Force planning. Ergonomics for space operations improved significantly due to these studies. The project also demonstrated the challenges of ambitious military space programs. Cost, inter-service competition, and rapidly advancing technology created unique hurdles. Lessons learned from program management informed later decision-making in aerospace projects. Future programs approached risk and budgeting with these lessons in mind. Although it never achieved orbit, Dyna-Soar inspired confidence that piloted spaceplanes were feasible. Its research provided a foundation for subsequent lifting body and shuttle programs. Engineers gained critical knowledge about reentry physics and thermal management. The project proved that human-operated spacecraft could combine speed, maneuverability, and survivability. The cancellation highlighted the shift from piloted military spaceplanes to missile and satellite-based systems. Strategic needs and cost-effectiveness drove this change. Nevertheless, the technical achievements remained influential. Many Dyna-Soar concepts were reused in later defense and NASA programs. Today, the X-20 is remembered as a pioneering but unrealized vision. Its legacy lives on in the Space Shuttle X-37B and other spaceplanes. Engineers and historians recognize its contributions to controlled reentry and orbital operations. The Dyna-Soar remains a symbol of Cold War ambition at the frontier of space technology.